I want you to do something for a second. If you're listening to this on a smartphone, or maybe if your phone is just sitting right next to you on the desk, I want you to just look at it.
Yeah, just give it a good look.
All right, like look closely at that dark, glossy rectangle. We tap, we swipe, we pinch, we zoom, and we interact with these screens, I mean, literally hundreds of times a day.
Oh, easily hundreds.
And we just treat it as this completely mundane, ordinary object in our lives. Like, you want to check the weather, you tap the glass, you want to text a friend, you tap the glass.
It's totally taken for granted.
Exactly. But you're actually holding, a paradox. Because to make that screen work, engineers had to forcefully fuse two sworn enemies of physics.
Two things that really, really hate each other.
Right. Complete transparency and high electrical conductivity. So today we're doing a deep dive into the source material to tear down the glass and show you the invisible wires inside.
It really is a contradiction that honestly feels like it just breaks the rules of the universe.
It kind of does, right?
It does, because in the natural world, transparency and conductivity, they do not want to exist in the same space.
Yeah.
You either get a window you can look through or a wire you can send power through. The fact that your phone screen does both simultaneously is just, it's an absolute triumph of material science.
Yeah, I was looking through the source material we gathered on the solid-state physics of these screens, and it just hit me how wild this is.
Yeah.
We are essentially demanding that engineers build us invisible wires.
That's exactly what it is.
We want all the electrical carrying capacity of like a thick copper cable, but we want it to be as completely clear as a freshly washed window pane.
And nature says no to that.
Right. So I'm incredibly excited to break down the everyday quantum mechanics that we are all just walking around with in our pockets.
Yeah.
Because once you understand why invisible wires shouldn't exist, you realize how brilliant this hack actually is.
Well, to really appreciate the solution, we have to dig into the problem first.
Okay, let's do it.
And the problem lies in the cold, hard rules of standard materials. The universe has a very strict divide. So let's look at the undisputed champions of conducting electricity, which are metals.
Right, like copper, aluminum, gold, silver.
Exactly.
If I want to wire a house, I'm obviously using copper. If I want to build a high-end audio cable, maybe I'm using gold. But I definitely can't see through any of them.
Not at all.
So why are the laws of physics so rigid about this? Like, why does being a good conductor automatically mean you are opaque?
It all comes down to atomic structure. So at a microscopic level, metals are packed full of what physicists call free electrons.
Free electrons, okay.
Yeah. Now, in most materials, electrons are tightly bound to their parent atoms. They stay put. But metals have this really unique lattice structure. The atoms form a rigid grid, but they essentially just surrender their outermost electrons.
So they just let them go.
Pretty much.
Okay.
These electrons detach and form this sort of communal sea of negative charge that just washes around the positively charged atomic cores.
Okay, so they aren't tied down to any specific atom anymore. They're just, like, roaming the halls.
That's a really solid way to visualize it. And because they are free to move, if you apply an electrical voltage to one end of a copper wire, those electrons just easily flow down the wire to the other end.
And that flow is the electricity.
Right, that continuous flow is what we call an electrical current. It's basically the ultimate open highway for energy.
Okay, I can picture that sea of free-roaming electrons carrying the charge. That makes sense. But, what does that have to do with light? Like, why can't I see through a sheet of aluminum foil?
This is where the physics get truly beautiful. The very thing that makes metals so good at conducting electricity.
For free electrons.
Yes, those free electrons are the exact same thing that makes them completely opaque. We have to remember what visible light actually is.
It's a wave, right.
Exactly. It's an electromagnetic wave. It carries energy and it oscillates or, vibrates at specific frequencies.
So a beam of light isn't just a straight line. It's more like a vibrating wave of energy just crashing into whatever it hits.
Yes. And when that oscillating wave of visible light hits the surface of a metal, it encounters that sea of free electrons.
Okay.
Now, electrons are highly, highly responsive to electromagnetic fields. So as the light wave hits them, the free electrons absorb that incoming energy and they begin to vibrate wildly.
Oh, wow.
And they vibrate perfectly in sync with the rhythm of the light waves.
So they start dancing to the exact rhythm of the incoming light.
That's a great way to put it. We call this phenomenon plasma oscillation.
Plasma oscillation.
Right. It's a collective, massive movement of the electron sea at the surface of the metal. Because these electrons are vibrating so intensely and so collectively, they act like an impenetrable kinetic shield.
So the light just can't get past them.
Exactly. The incoming light waves simply cannot penetrate the material. The vibrating electrons absorb the wave's energy and instantly re-emit it.
Meaning they bounce the light wave backward, away from the metal.
Right.
So the light is completely rejected, it bounces back entirely.
100%. And this raises a really fascinating point about how we perceive the world around us.
What do you mean?
Well, this total reflection of visible light is the literal scientific definition of metallic luster.
That's what makes things shiny?
It is exactly why metals are shiny. When you look at a silver mirror or like a polished gold ring, you are not just seeing a color. You are seeing plasma oscillation in real time.
That is wild.
Yeah, you are watching free electrons form a shield and bounce the ambient light of the room straight back into your eyes.
Okay, I want to use an analogy here because visualizing these microscopic interactions is like so crucial for the listener.
Go for it.
Think of these free electrons as bouncers at an incredibly exclusive, incredibly crowded nightclub.
Okay, I like this. Let's follow that logic. How does the light fit in?
So the visible light, the light waves trying to pass through the material, there are a massive crowd of guests trying to get into the club.
Yeah.
But the club is completely surrounded by these highly energetic, incredibly active bouncers, the free electrons. The moment the light waves try to approach the door, the bouncers start physically blocking them.
Because they're responsive to the field.
Right, but they don't just stand there like a brick wall. They match the guests' movements step for step, dancing wildly in front of the entrance, physically absorbing the momentum of the crowd and pouncing the guests right back out onto the street.
So the light never even gets past the velvet rope.
Exactly.
That analogy holds up remarkably well, actually, especially because it highlights the kinetic nature of the defense.
Right, because they're moving.
Yeah, the bouncers aren't a static wall, they are an active moving barrier. And because they are so efficient at bouncing those light guests away, the building itself looks incredibly shiny from the outside. That's your metallic luster.
Man, that's so cool. But then, we look at the other side of the material divide. We look at materials like glass or clear plastic. They have to operate under a completely different set of rules.
They absolutely do. Glass and plastic are fundamentally different at the atomic level.
So,
They rely on covalent bonds, which basically means their electrons are tightly bound to specific atoms. They do not have that communal sea of free electrons.
they're stuck.
Right. Every single electron has a specific job holding the molecules together, so they are locked firmly in place.
Okay, so in our nightclub scenario, the bouncers are all tied to chairs inside the club. They physically can't move to the door.
Which leaves the entrance completely unguarded.
Wow.
So when the visible light waves arrive at the glass nightclub, there are no mobile bouncers to stop them. The light waves just stroll right past the lockdown electrons, navigate through the empty spaces in the atomic structure, and come out the other side.
And that is why glass is transparent.
Precisely. It simply lacks the mobile defense system required to stop an electromagnetic wave.
But I mean, there is a massive trade-off
Oh, a huge one.
because all those electrons are tied to their chairs and locked in place. If you try to push an electrical current through the glass, absolutely nothing happens, right?
Correct. There are no free electrons to detach and carry the electrical charge down the line.
So that's the core of the problem. Glass is wonderfully transparent, but it is a terrible conductor of electricity. It's an insulator.
Yes.
So wait, if metals inherently bounce light away because of the very things that make them conductive, the free electrons, isn't a transparent metal physically impossible?
It certainly seems that way.
Like if you need free electrons to conduct electricity, but free electrons automatically block visible light, you are caught in an inescapable paradox. A transparent touchscreen just shouldn't exist.
By the standard rules of classical materials, you are entirely correct. It is a massive contradiction, and for a long time, material scientists faced exactly this wall.
But I'm guessing they didn't just give up.
No, engineers don't tend to accept impossible for an answer. They realized that if they couldn't find a natural material that did both, they would have to basically hack the laws of physics at the atomic level to create a hybrid.
And this brings us to the magic material hiding inside every single smartphone screen. It's an acronym I saw repeated constantly in the source material we pulled. ITO.
Yes, ITO. Indium tin oxide.
Indium tin oxide.
Indium tin oxide is literally the linchpin of the modern digital age. It belongs to a very special class of materials known as transparent conductive oxides.
Let's break down exactly how ITO pulls off this magic trick because It involves some seriously elegant quantum mechanics. According to the research, we have to start with the base material before the tin even enters the picture.
Right, the foundation.
The foundation is a chemical compound called indium oxide.
Yes, indium oxide, chemically written as N2O3. This is our starting point. And indium oxide has a specific property that we need to dissect, which requires us to introduce a foundational concept in solid-state physics.
Hang on.
It's called a band gap.
A band gap. Yeah, I spent a lot of time staring at this term in the source material. It's usually represented by a capital E with a little subscript G, right? So E sub G.
That's the one.
What exactly is a band gap in, like, physical terms?
Think of the band gap as an energy barrier or a forbidden zone. In solid-state physics, electrons in a crystal lattice can only exist at certain specific energy levels.
Okay.
We group these levels into bands. There is a lower energy band called the valence band, where electrons are stuck to their atoms, helping to hold the material together.
Like the bouncers tied to their chairs in the glass.
Exactly. Then there is a higher energy band, the conduction band, where electrons are free to move and carry an electrical current.
Like the bouncers roaming free in the metal.
Right, again. The space between these two bands is the gap. It's a literal void where the laws of quantum mechanics forbid electrons from existing.
Wait, so they just can't be there at all?
Nope. So for an electron to jump from being stuck in the lower band to being free in the upper band, it needs a burst of incoming energy to leap entirely across this forbidden void.
If it doesn't get enough energy, it just stays stuck.
Exactly. And different materials have different sized gaps. Metals essentially have no gap at all.
Which is why they always have free electrons.
Right, their bands overlap. Insulators, on the other hand, have massive gaps.
Okay.
Now let's look at the numbers for indium oxide because this is where the transparency actually originates. We measure this energy gap in a unit called electron volts, or EV.
Electron volts, got it.
Indium oxide has a remarkably large band gap of over 3.5 electron volts.
Okay, so 3.5 EV is the size of the jump required for an electron to get free. Now, what about the visible light trying to get through the phone screen? Because that light is carrying energy too, right?
It is. Visible light, whether it's the backlight of your LCD or OLED screen or just the ambient light from the sun, is a spectrum of energy. But compared to atomic bonds, the energy of visible light is actually relatively weak. The photons, or particles of visible light, only carry an energy ranging from about 1.6 to 3.1 electron volts, depending on the color.
1.6 to 3.1. So red light is on the lower end, blue light is on the higher end.
You got it.
Okay, wait. I see the math here. The strongest visible light coming in, the blue light, maxes out at 3.1 EV.
Correct.
But the band gap, the energy barrier of the indium oxide, is 3.5 EV.
Yes.
The light simply isn't strong enough to bridge the gap.
You're hitting on the absolute core mechanism there. Because the visible light's maximum energy is too weak to force any of the indium oxide's electrons to jump that massive gap, the light cannot interact with the material's electrons in any meaningful way.
It just doesn't have the juice.
Right. Quantum mechanics dictates that if an electron cannot reach a valid energy state, it will not absorb the incoming energy at all.
I was trying to come up with a visual for this, and initially I thought about like a hurdle on a track, but that doesn't quite work, because if a hurdle is too high, the runner just crashes into it, you know?
That's true.
A much better way to picture this band gap is a staircase with a massive missing step right in the middle.
Oh, I like that. Let's explore that. How does the light interact with the staircase?
So the visible light is someone trying to climb the stairs, but they only have enough energy, enough leg strength to step up, say, 3.1 feet.
Okay.
However, the missing step in our indium oxide staircase creates a gap that is 3.5 feet high. If the climber tries to step up, their foot will literally land in empty space.
Right. They can't reach the next solid step.
Exactly. And because quantum rules say you can't stand in empty space, you can't just hang out in the forbidden zone, the climber simply cannot make the jump.
Yeah.
So the incoming light wave doesn't transfer any of its energy to the staircase at all. It just gives up and passes right by it like a ghost.
That is a much, much more accurate quantum visualization. If the energy isn't sufficient to reach an allowed state, the interaction simply doesn't happen. The light isn't absorbed, it isn't reflected, it just continues on its path. So to visible light, indium oxide is completely transparent. It's a 100% pass-through.
So step one is complete. We have a clear piece of material,
We do.
but we still have our original problem, right?
We certainly do.
If all the electrons are stuck in that lower energy band and the light can't force them to jump, and the material naturally has no free electrons in the conduction band, then the indium oxide doesn't conduct electricity.
Nope, it's an insulator at this point.
We have a beautiful transparent piece of glass, basically, but we do not have our invisible wires yet.
And this is where the engineers applied the actual hack. This is where the T in ITO comes in. Tin.
The process is called doping, which, sounds nefarious, like sports cheating or something.
It does sound a bit shady, but in material science, it's a very precise manipulation. Doping is the intentional introduction of impurities into an extremely pure crystal lattice to fundamentally alter its electrical properties.
Okay, so how did they do it here?
The scientists took this perfectly clear indium oxide and they mixed in a tiny, highly calculated percentage of tin atoms.
Like, how much are we talking?
We are talking just a few percent of the total atomic makeup. It's a very small amount.
I really want to understand the physical mechanism of this. Like, what actually happens when a tin atom gets forced into an indium oxide crystal?
We have to look at the chemistry for that. Indium atoms naturally have 3 valence electrons.
So there's the outer electron group.
Exactly. 3 electrons in their outer shell that they use to bond with oxygen to form the crystal lattice. The entire crystal is structurally happy and balanced with these bonds.
Okay, everything is stable.
But tin atoms are slightly different. Tin has 4 valence electrons.
So it brings a +1 to a party where all the seats are already taken.
Exactly right. When you force a tin atom to substitute for an indium atom in the crystal grid, it uses 3 of its electrons to perfectly mimic the indium and lock into the surrounding oxygen atoms.
Right.
But it has that 4th electron left over.
The +1.
The +1. And that extra electron has nowhere to bond. It doesn't fit into the chemical structure of the lattice at all.
So what happens to it?
Because of this atomic tension, that extra electron is essentially cast out. It requires almost 0 energy to detach from the tin atom, and it just gets pushed straight up into the conduction band.
Oh!
It becomes a free electron.
Wait, so by sprinkling in millions of tin atoms, they are forcefully injecting millions of free electrons into the material.
That's the hack.
But wait. We established earlier that free electrons are the bouncers.
We did?
We said they are the things that cause plasma oscillation and block light. So if we just filled the clear indium oxide with a bunch of bouncers, why doesn't it instantly turn dark and metallic?
And this is the true miracle of ITO. This is a brilliant manipulation of the electromagnetic spectrum.
How does it not just turn into a mirror?
It all comes down to the density of the free electrons.
The density.
Yeah. In a standard metal, like copper, the density of free electrons is astronomically high. There are so many of them. That massive density means the plasma oscillation, the rhythm at which the electrons vibrate, is tuned specifically to block visible light and ultraviolet light.
Okay.
But in ITO, the engineers tightly control the doping process.
They controlled exactly how many bouncers are hired.
Right. They add just enough tin to provide the free electrons needed to conduct electricity effectively, but the density of those electrons is much, much lower than in a pure metal.
So there are fewer bouncers.
Exactly. And because the density is lower, the plasma oscillation frequency, the speed at which the electron C vibrates, is shifted downward.
It'll work.
It shifts completely out of the visible light spectrum and down into the infrared spectrum.
This is wild. So the bouncers are there, they are highly mobile, and they are fully capable of carrying an electrical current.
Yes.
But they are vibrating at a frequency that visible light doesn't even notice.
Exactly. Visible light is oscillating too fast for the ITO's electron C to react to it.
That is incredible.
So when visible light hits the ITO, it still sees that massive 3.5 EV band gap we talked about.
Right.
It still realizes it can't interact with the bound electrons, and it still ignores the relatively sparse, slow-vibrating free electrons. So the visible light passes right through.
Wow.
However, if you shine infrared light at your phone screen, which is a lower frequency, the screen actually acts like a mirror and bounces it back because the ITO is opaque to infrared.
I am genuinely blown away by the sheer elegance of this. Like, by specifically manipulating the atomic lattice, scientists created a material that visible light treats as an empty, void-like glass. The electrical currents treat as an open, free-flowing, highway-like metal.
It's incredible, isn't it?
They didn't just find a magical material in the ground, they mathematically engineered a loophole in physics.
They absolutely did. And how they apply it to your phone is a marvel of modern manufacturing, too.
How'd they get it in there?
Well, they don't cast a solid block of ITO. They use a process like sputtering in a vacuum chamber to lay down a nanometer-thin grid of this material right beneath the protective glass of your screen.
And when we say nanometer thin, we are talking microscopic.
Oh, completely. It's a layer so thin It's entirely invisible to the naked eye. It is a literal grid of transparent wiring laid over the entire display area of your phone, perfectly aligned and totally unseen.
So we have solved the first major hurdle. We have successfully created transparent wires.
Check.
We have our grid of ITO sitting just beneath the glass, allowing the screen's light to shine up into our eyes, while possessing the ability to carry an electrical charge. The material contradiction is officially conquered.
It is,
Well-
but having a wire is really only half the battle.
Right, because a wire is just a dumb conduit for electricity. Like, how does this static grid actually know where my finger is touching it? How does it translate a physical tap on a piece of glass into a highly specific coordinate on a map?
Yeah, that takes us from the realm of material science and solid-state physics into the realm of electrical engineering and sensory design.
Okay, let's get into it.
The mechanism we are talking about here is called projected capacitive touch.
Projected capacitive touch.
That's the one.
When I was looking into how this grid tracks our fingers, the most fascinating concept I found in the sources was this idea of microscopic pools of electricity.
I love that visualization.
To understand this, we have to realize that a smartphone screen is not just one big continuous sensor. It's actually a giant microscopic collection of individual electronic components called capacitors.
Right, and since we're dealing with capacitors here, let's establish exactly what they're doing in this context. A capacitor is fundamentally different from a battery.
How so?
It doesn't generate power chemically. It is simply a physical architecture designed to store electrical energy as an electrostatic field. It just holds a tiny pool of static electricity.
Okay. And the physical architecture of that capacitor dictates exactly how much electricity it can hold.
Exactly.
I was staring at this one equation in the research, and at first it looked like absolute alphabet soup.
Math usually does.
Right. But it actually perfectly explains why our phones work and why they sometimes fail. The equation is C equals epsilon times A divided by D.
Yes. Let's translate those variables into the physical reality of the touchscreen so it doesn't just sound like a math class.
Please do.
C stands for capacitance. That is the total size of the electrical pool that can be stored at any given point.
Okay, so C is the ultimate size of our electrical puddle.
Now, what determines that size? On the other side of the equation, we have A for area.
Area.
A capacitor is usually made of two conductive pieces. The larger the physical surface area of those conductive pieces, the more electric charge they can hold. Think of it like a bucket. A wider bucket simply holds more water.
That makes sense. Area is straightforward. Bigger area, bigger puddle.
Then we divide that by D, which stands for distance. And this is the critical variable.
This is between what?
The two conductive pieces in a capacitor. They are close to each other, but they never ever touch. The D is the physical space between them. The closer they are together without touching, the stronger the attraction between the positive and negative charges, and the higher the capacity to hold that charge.
And if they move apart?
If you pull the conductive pieces further apart, the attraction weakens exponentially and the capacity drops.
So area and distance are the geometric factors. Bigger area means bigger capacity, larger distance means smaller capacity.
Exactly.
But then there is that Greek letter, epsilon.
Epsilon. Epsilon represents permittivity. This isn't about geometry, it's about the material itself.
Permittivity, what does that mean?
It measures how easily a specific material, the stuff that exists between and around the conductive pieces, allows an electric field to form within it.
How does a material actually do that, though?
It comes down to molecules. Some materials are made of polar molecules, dipoles, that have a slightly positive end and a slightly negative end. Water is a perfect example.
Okay, water is polar.
Right. When you apply an electric field to water, all those little water molecules physically rotate and align themselves with the field.
They line up.
Yes, and this alignment actually stores energy, meaning pure water has a very high permittivity. It loves holding an electric field. Air, on the other hand, has very few molecules to align, so it has a very low permittivity.
So if you introduce a material with high permittivity near the capacitor, it instantly boosts the total capacity C. The whole system can suddenly hold more charge.
That's the formula in a nutshell. Total capacity is a delicate, continuous balance of the area, the distance, and the permittivity of the materials involved.
Okay, I have the physics of the equation in my head. Now, how do we map this math onto the physical reality of the nanometer-thin ITO grid sitting under my phone screen?
Picture the ITO grid laid out like a highly organized city map viewed from above.
Okay.
You have transparent wires running vertically north to south, and a completely separate layer of transparent wires running horizontally east to west.
Like avenues and streets.
Right. And where an avenue crosses over a street, you have an intersection. But here is the critical engineering detail. The vertical wires and the horizontal wires are separated by a microscopic layer of insulation.
They don't touch.
They never physically touch each other. There is a precise engineered distance between them.
Wait, that's the D in our equation. The precise distance separating the conductive avenues from the conductive streets.
Yes. And because you have two conductive wires separated by a specific distance, every single intersection on that entire display forms a tiny individual capacitor.
So a modern phone screen is essentially millions of tiny microscopic intersections, meaning millions of individual capacitors.
When you wake your phone up, the battery sends a very weak, continuous scanning voltage through the entire ITO grid.
Okay.
This voltage charges up every single intersection. So, to use our earlier visualization, at every intersection of every street and avenue on this microscopic city map, a tiny, invisible puddle of static electricity forms.
A grid of millions of microscopic electrical puddles, just sitting there under the glass, humming with a tiny baseline charge.
Sitting there, completely stable, until you introduce a disruption.
Okay, so this is the part of the process where I initially got confused reading the sources.
Where did you get stuck?
Well, we have this beautiful grid of electric puddles sitting under the glass. But when I use my phone, my finger isn't touching the ITO wires.
No, it's not.
I'm tapping on a solid, highly durable piece of chemically strengthened glass-like Gorilla Glass. And glass, as we established way back when we talked about bouncers and nightclubs, is an insulator.
It is.
Electrons are locked down. It blocks the flow of electricity.
Oh.
So how on earth does the invisible grid know I'm there if the glass is physically blocking my finger from actually touching the puddles?
It's a very common misconception to view an insulator as an absolute wall for everything, while glass is an excellent insulator that blocks the flow of an electric current.
Meaning it prevents the actual movement of electrons from the wire into my finger.
Exactly. It prevents current, but it does not block an electric field.
Let's clarify the difference, because that distinction is everything.
Think about magnetism. If you put a thick piece of glass over a strong refrigerator magnet, the magnetic field doesn't stop at the glass.
Right, it goes right through.
It easily permeates right through it. You can stick another magnet to the top of the glass, and they will pull toward each other through the solid material.
Okay, I can visualize that.
Electric fields operate in a very similar way. The invisible puddles of static electricity at the ITO intersections don't just sit flat, they generate a subtle electric field that arcs upward. Engineers call this a fringing field.
A fringing field. So the field is essentially bowing upward, radiating out in 3 dimensions.
Because the vertical and horizontal wires are laid out side by side on a microscopic plane, the electric field lines between them arc up in a sort of half-circle geometry.
And that field goes through the glass.
That arcing electric field easily permeates right through the insulating glass layer, and it reaches slightly past the surface of the screen out into the open air.
Okay, so the puddles are safely trapped under the glass, but their aura, their arcing electric field, is radiating just slightly above the surface of the glass where my finger actually operates.
You are interacting with the aura, not the puddle. And this is where the human body enters the equation and fundamentally alters the physics of the system.
This is where the story gets a bit mind-blowing to me. The concept of the electricity thief.
It's a great term.
We have to remind ourselves of a basic biological reality. The human body is a spectacular conductor of electricity.
We are largely composed of water, and that water is completely saturated with dissolved salts, minerals, and electrolytes.
Like sodium and potassium ions.
Right, so from the perspective of solid-state electronics, your finger is basically a highly conductive, fleshy, ion-filled electrode.
Not the most flattering description of my hand, but scientifically accurate, I guess.
And crucially, human skin has a very high permittivity. Remember our epsilon value.
From the equation, yes.
Mhm.
Because of the water molecule.
Because of all that water, which is made of highly polar molecules, your body is extremely good at interacting with and holding an electric field.
Let's put this all together in ultra slow motion. My phone is on. The ITO grid is charged. The microscopic puddles of electricity are sitting at the millions of intersections, projecting their fringing electric fields up through the Gorilla Glass.
Right.
Now, my highly conductive, high permittivity, fleshy electrode of a finger descends toward the screen to, type a letter. What happens at the exact nanosecond of touch?
As your finger approaches the surface of the glass, it enters that invisible arcsing electric field radiating from the specific puddles directly beneath it.
Okay.
Because your finger is so conductive and has such high permittivity, the electric field is irresistibly drawn to it. The field lines literally bend toward your finger. The field couples with your body.
It reaches out and grabs my finger.
It does. And because your body is so massive and so conductive compared to the microscopic nanometer-thin ITO wires, your body effectively acts like an electrical sponge.
A sponge.
When the fringing field connects with your finger, your body effectively draws away a tiny, tiny portion of the electrostatic charge from that specific microscopic pool beneath the glass. You act as a temporary sink for the charge.
I literally steal some of the electricity without ever actually touching the wire.
You become a localized electricity thief. And the moment your finger steals that tiny bit of charge, we have to look back at our equation.
C equals epsilon times A over D.
The overall permittivity, the epsilon of the localized environment, has suddenly spiked because a watery human finger just entered the field.
The environment changed, so the capacity C, the size of the pool, suddenly fluctuates at that exact intersection. The puddle suddenly registers a drop in charge because my finger drank some of its aura.
The physical act of you pressing your finger against the glass causes an instantaneous, measurable drop in the electrical voltage at the specific X and Y coordinates where your finger landed.
But wait, the grid itself is just a passive piece of transparent wire. How does the phone actually process that the pool just changed size?
The grid is passive, but it is wired into the brain of the touchscreen. Connected to the edges of this entire ITO grid is a microscopic piece of silicon called the Control IC, the Integrated Circuit Chip.
I try to picture the Control IC chip as an incredibly hypervigilant, heavily caffeinated security guard sitting in a control room watching a massive bank of monitors. And each monitor represents one microscopic intersection on the grid.
That's a fun visual, but let's scale it to reality because it's even crazier. The security guard does not just casually watch the monitors.
What does he do?
The IC chip multiplexes the signals, meaning it rapidly sends pulses down the rows and listens on the columns. It sweeps its attention across the entire grid, checking the exact electrical baseline charge of every single puddle, one by one.
And it has to do this constantly to know what the grid looks like when it's a piece.
It sweeps the entire grid, all millions of intersections, hundreds of times every single second. Most modern touchscreens have a touch sampling rate of 120 Hz, 240 Hz, or even higher for gaming phones.
Wait, so 240 times every second it checks every single puddle?
It's constantly pulsing the grid. Puddle 1 is full, puddle 2 is full, puddle 3 is full, over and over and over. Then your finger comes down, you touch the M key on your digital keyboard, your finger enters the fringing field and steals a tiny sip of electricity from a cluster of puddles directly under the M key. The capacity at that specific physical location fluctuates.
And the hyper-vigilant security guard notices instantly.
On his very next sweep, literally a fraction of a millisecond later, he sees the voltage drop. The IC chip flags an anomaly.
Like, alert. The puddles at intersection X450, Y800 just got robbed.
Exactly. And because the IC chip knows the exact physical address of every puddle it monitors,
it mathematically calculates the exact centroid of the theft, pinpointing the center of your finger.
It instantly sends a digital coordinate signal to the phone's main processor. Touch event registered at coordinate X450, Y800.
And then the operating system processor references those coordinates against what is currently displayed on the screen, realizes that coordinate aligns with the M key on the keyboard app, and boom, the letter M appears in your text message.
You got it.
I need to pause and dwell on the sheer processing speed this requires.
Yeah.
Think about how fast you type a text message.
It's a blur.
Your thumb feels like it's barely grazing the glass, moving incredibly fast. But in the fraction of a second your thumb was near the screen, the IC chip scanned the entire grid dozens of times, detected a microscopic fluctuation in charge capacity caused by the polar water molecules in your skin, triangulated the center of that theft, and translated it into a software action.
It is an orchestrated symphony of solid-state physics, chemistry, and electrical engineering happening faster than human perception.
But what really gets me, like the philosophical implication of this, is that we, our physical biological bodies, are literally becoming a physical component of the electronic circuit every time we send an emoji.
Yes.
We aren't just pushing plastic buttons that click together to close a circuit like old typewriter keys.
No, the circuit remains completely open and incomplete without you. You are the missing variable in the equation.
We are manipulating microscopic electric fields with the conductive properties of our own flesh. Our bodies are the biological key that makes the machine function. It's basically a bioelectrical interface disguised as a piece of glass.
When you frame it that way, you really begin to see why touchscreens feel so intuitive to humans, almost instinctual.
They do.
They are directly reacting to our body's inherent electrical nature. The screen is literally feeling for our presence.
Which perfectly sets up why it is so insanely maddening when the screen ignores us.
Oh, yeah.
If the entire system relies on our bodies acting as a highly conductive electricity thief, what happens when we change the environment? I was applying the capacitance formula C equals epsilon times A over D2 everyday touchscreen failures, and the math explains the frustration perfectly.
Let's run some scenarios then. It's the ultimate test of whether we understand the physics we just looked at.
Okay, scenario 1. We've all been there. It's late January. It's freezing outside. You're wearing a nice pair of thick wool winter gloves, or maybe like heavy leather gloves.
Okay, setting the scene.
Your phone vibrates in your pocket. You pull it out. You aggressively swipe the screen to answer the call, and absolutely nothing happens. The phone completely ignores you.
Completely unresponsive no matter how hard you press.
I always used to just push harder, thinking it was a pressure thing. Like if I just push my thumb harder, it'll register. But as we've learned, touchscreens do not care about physical pressure at all.
Not even a little bit. They care about electric fields.
So let's look at the gloves. Wool and leather are natural insulators. Their electrons are locked down. They do not conduct electricity.
Okay, they are insulators, but your finger is still inside the glove.
Right.
The conductive, watery flesh, the electricity thief, is still present. Why doesn't the phone feel it?
I realized it all comes down to the D in our equation. Distance.
The physical space.
The capacitor's ability to hold a charge and my finger's ability to steal that charge is entirely dependent on the physical distance between the ITO grid and my conductive skin.
Yes.
The fringing electric field radiating up from the glass is incredibly weak. It only arcs a very, very small distance above the surface of the screen.
Ah. And what does the wool glove do to that distance?
The wool glove is physically thick. It adds several millimeters of bulk between my skin and the glass. Wearing the glove increases the distance, the D, far beyond the reach of the electric field's aura.
So you're out of range.
My finger is essentially hovering miles above the field, unable to penetrate it, and therefore completely unable to steal the electricity.
And if you don't steal the electricity,
The puddle doesn't change size, the IC chip sees nothing abnormal on its sweep, and the phone feels absolutely nothing.
the math proves the frustration perfectly. The D became too large, so the C couldn't fluctuate.
Exactly. But, technology adapts. You can go to the store and buy those special smartphone-compatible winter gloves.
The ones that look like normal knit gloves, but the tips of the thumb and index finger are a slightly different color gray.
Yeah. And miraculously, you can type with them on. I always wondered what the trick was there. Are they just thinner at the fingertips?
No, they don't solve the problem by changing the thickness of the glove, because then your hands would freeze, which defeats the purpose. They solve it with material science. They weave conductive threads directly into the fabric of the fingertips.
Conductive threads.
Yeah. They take standard nylon or polyester fibers and literally coat them in a microscopic layer of real metal, usually silver or copper.
Wait, so there is actual metal wiring woven into the tips of the gloves?
Yes, and those metallic threads act as a direct physical electrical bridge.
Ooh.
When your warm conductive finger is inside the glove, your skin touches the inside of the metallic thread. The metallic thread passes all the way through the thick insulating fabric to the outside of the glove, which physically touches the glass.
It's literally an extension cord for my finger's conductivity.
That's exactly what it is. It channels your body's natural electric capacity straight through the insulating wool, bypassing the distance problem entirely.
That's brilliant.
It delivers your finger's electrical signature directly into the fringing field on the surface of the glass, allowing the theft of the electric pool to happen just as if your bare skin was touching it.
That makes so much sense. Okay, let's look at another very common failure scenario too.
Let's hear it.
Say you are indoors, you don't have gloves on, but you try to tap the screen with the tip of your fingernail. Or maybe you grab a standard plastic ballpoint pen off your desk and try to use it as a makeshift stylus.
And again, the screen is dead to the world.
Right. This failure requires us to look at a different variable in the capacitance equation. Why doesn't a fingernail work?
Well, let's look at it. The distance D isn't the problem here, is it?
No, my fingernail is physically tapping directly on the glass. The distance is basically zero. It's as close as it can possibly get to the fringing field.
You're right, the distance is optimal. The failure here lies in the epsilon, the permittivity.
The material's ability to hold an electric charge.
Exactly. We established that human skin is full of water, full of highly polar molecules and electrolytes. It has an incredibly high permittivity, making it fantastic at interacting with and absorbing electric fields.
But what is a fingernail actually made of?
Fingernails are made of keratin. It's essentially dead, dried, densely packed protein.
Completely dry, almost zero moisture. And because it lacks those polar water molecules, its permittivity, its epsilon value, is abysmally low.
And the same principle applies to the hard plastic of a ballpoint pen.
Right, plastic is a classic insulator with terrible permittivity. It doesn't have the molecular structure to interact with the static electric field at all.
So even though the keratin nail or the plastic pen is physically touching the glass right in the middle of the electric aura,
They simply lack the physical capability to disrupt the field. They cannot hold the charge. They are mathematically invisible to the capacitor.
Yep. The electric pool just ignores the plastic pen entirely. No electricity is stolen, the puddle remains full, and the security guard registers no change.
So to summarize the engineering reality here, it's essentially an incredibly specific Goldilocks situation.
It really is.
For the touchscreen to even acknowledge your existence, you need a material that can actively hold an electrical charge, requiring high permittivity, like our ion-rich skin. But it also has to be physically positioned close enough to the microscopic grid, minimizing the distance, to physically interact with the short-range fringing field.
You need the right material at the exact right distance to disrupt an invisible grid of quantum-engineered pools.
It is just a massive testament to the brilliance of the engineering that this incredibly delicate dance works so flawlessly, billions of times a day, that we just assume it's a dumb piece of glass.
It is the ultimate invisible technology. When it works perfectly, you don't even notice it exists.
As we start to bring this deep dive full circle, I want to just sit back and look at the massive picture we've painted today from all our sources.
It's a big picture.
We started by looking at the seemingly ordinary phone in our hands, and we uncovered the invisible war between light waves and electron seeds.
The paradox of the transparent metal, solved by bandgap engineering.
The fact that engineers figured out how to build an atomic staircase with the missing middle step, just large enough that visible light passes right through without interacting, creating a perfectly transparent window.
But then, they purposefully infected that crystal lattice with tin atoms.
Right, forcing millions of homeless electrons into the conduction band, turning that clear window into a highly conductive metal wire whose plasma oscillation is perfectly tuned to ignore the visible spectrum.
It is a paradox solved by controlling materials at the atomic level, essentially bending quantum mechanics to our will.
And then they took those microscopic transparent wires, laid them out in a massive grid of streets and avenues that never actually touch, and applied a voltage to create millions of tiny invisible pools of static electricity waiting patiently under a sheet of Gorilla Glass.
The physics of projected capacitance, building an array of millions of microscopic sensors.
Where the final, most crucial piece of the puzzle isn't actually inside the phone at all.
No, it's us.
It's our biology, our conductive, water-filled bodies reaching out or penetrating the fringing electric fields and acting as localized electricity thieves hundreds of times a second, allowing a microscopic silicon security guard to pinpoint our exact intent on a sheet of glass.
It really emphasizes the most powerful conclusion from the solid-state physics research we reviewed. When you look at a smartphone touchscreen, you aren't just looking at a convenient interface or a disposable piece of consumer electronics.
What are you looking at?
You are looking at the absolute pinnacle of human crystal control and material science.
We literally carry the greatest hits of the last 100 years of solid-state physics in our pockets every single day.
And we use this pinnacle of human achievement to, argue with strangers on the internet or look at pictures of cats.
Which is arguably the most human thing we could possibly do with a scientific miracle. But understanding the depth of that miracle makes the mundane act of swiping so much more fascinating.
It totally recontextualizes our relationship with the devices we touch constantly.
It absolutely does. And I want to leave you, the listener, with a final mind-expanding thought that builds on everything we just discussed. We are highly visual creatures. We trust what we can see.
But your phone operates entirely in the invisible world of fields and frequencies.
Exactly. Now that you know your screen works by projecting invisible electrical auras that your biology dynamically interacts with hundreds of times a second, think about this.
Let's hear it.
Every time you are sitting on the couch, idly scrolling through your feed, you aren't just pushing against a dead piece of glass. You are physically dancing with a microscopic, quantum-engineered electric field. You are manipulating solid-state physics just by double-tapping a photo. You are an active biological participant in an electrical circuit that bridges the gap between human flesh and transparent metal.
That's a powerful thought.
Keep that in mind the next time your screen smudges.